Good day, stats students. So today we're going to go over section 10.2 part 1, and this part just sort of gets you going on how to interpret the hypothesis test and how to interpret more importantly the confidence interval, because that's actually the harder thing to do if you don't pay attention. All right. So we're not going to go over specific problems here, but this section, this introductory, if you will, to the two sample t-test is really important to pay attention to. If you pay close attention, it'll make doing the interpretation so much easier and doing the hypothesis so much easier. All right, and so if you have any issues with this, take a look at the commentary. If you're still having issues, please email me, let me know. Okay, but I think if you pay close attention to what's going on here, and you listen to what I have to say, hopefully it'll go okay for you. All right, so we can compare two groups on a quantitative response variable by comparing their means. All right, and so the response variable has to be quantitative, all right, because we are talking about comparing two means. So suppose we are interested in the difference between the mean price of a house in neighborhood 1 and the mean price of a house in neighborhood 2. Suppose we want to decide whether the mean house prices are different by location. Okay. So we'll make population 1 neighborhood 1 and obviously population 2 neighborhood 2. Now, here's the thing, is that in real life, if you're doing this, and yes, people do this test all the time in real life. Okay, we don't just run this in academia. All right, this is done all the time, and it really does not matter which group, which population, if you will, you make population number 1. All right, it doesn't matter. So if you were comparing males and females, you can make males population 1, you can make females population 1. It doesn't matter, okay? However, in the problems that we're doing in class, especially like in WebAssign or for the exam, please leave population 1 as is. So we're going to define which one is population number 1, all right? Leave it as is, all right? If you're doing this by yourself, you can make population 1 whatever you want to, okay? All right, moving on. The following denotes the means of the variable house price for the two populations. And so, since we have two populations, we're going to need a mu1 and we're going to need a mu2. All right, and so because we're going to want to compare these two things. All right, and so we talked about how we could have two populations in the introductory part of this thing. Okay, of chapter 10. And so here we're introducing that, okay, we're going to need some extended notation. But the good thing is that mu still means the same thing. It's still the population mean. It's just that it's the population mean for the first group or the first population. And mu2 is for the second population. The hypothesis test can be carried out by doing the following. All right, so we take independent and random, and by the way, this could apply also to confidence intervals, it doesn't matter. Independently and randomly take a sample of house prices in neighborhood 1 and a sample of house prices in neighborhood 2. Okay, so you got population 1, population 2, you take a random sample from each group. Okay, and then you would compute. Now, probably we're going to have the computer do this for us, so we're going to probably use computer output for this, but could we compute this? Yeah, probably. Okay, so we would go ahead and compute X bar for the first group. And so, okay, so we have population 1. We took a random sample from there, and then we calculated X bar, the sample mean from it. All right, and so, okay, we could do that. Probably we're going to use the computer to help us with that. Okay, but we're going to designate that as X bar 1. And then we got, obviously, then X bar 2. All right. So now this is what you want to highlight. Okay. So if you're following along with your notes, you might want to highlight this. What we're then going to do to compare mu1 and mu2, believe it or not, we will be doing an inference on the parameter mu1 minus mu2. And so the parameter is not two separate things. It is just one parameter. I know it looks like that we have 2, but since we are doing the subtraction between the two, mu1 and mu2, that only makes it one parameter. Okay, so that means we're only going to make one confidence interval. We're only going to do one hypothesis test. And what is it going to be on? Mu1 minus mu2. And I'm going to keep on saying that over and over and over again to make sure that you got it. Okay, and so there's only one parameter here, mu1 minus mu2. Okay, so we're not going to make two separate confidence intervals. We're not going to make a confidence interval for mu1. We're not going to make a separate one for mu2. We are going to make one and somehow figure out, based upon that one confidence interval and that one hypothesis test, if mu1 is greater or mu2 greater, or we may not be able to tell the difference based upon our random samples. Okay, so keep that in mind. All right. Now, to make an inference about the difference between population means, we need to learn about the variable of the sampling distribution of x bar 1 minus x bar 2. Now, you might want to highlight that. Why? Because that is the point estimate for the confidence interval that we're going to create. I'm probably going to have the computer create it for us. Okay, and that's also going to be the numerator in the test statistic. Okay, so that's a pretty important number, and that number actually shows up in just about any computer program that you use to run the two-sample t-test. All right, so x bar 1 minus x bar 2 is a pretty important number, but we need to learn about the variability of how x bar 1 minus x bar 2 might vary from these samples. Okay. All right, so the difference is attained from sample data. It will vary from sample to sample just like any other statistic. And so that x bar 1 minus x bar 2, that's our statistic here. Okay, so the variation, the standard error of the sampling distribution of x bar 1 minus x bar 2. Now don't cringe. Okay, don't go too crazy with this. Okay, there it is. Okay, so this is telling us how x bar 1 minus x bar 2 varies from sample to sample. Okay, now what are we talking about here? Well, if we could, this is easier than what you think. Now, one, in WebAssign, we might have you calculate this once or twice. Okay, on the test, on the exam, on the final, we're probably not going to have you calculate this. Okay, but could we? I think so. Okay, so what is this? Well, all right, so S1. That is the sample standard deviation from the first sample. That's all. And then that gets what? Squared. That's not hard to do, right? You can do that in your calculator. And then you divide that by the sample size from that first group, okay? And then you add that to the sample standard deviation from the second group and you square that number. And you divide by the sample size from that group, and then after you do the addition between the two, then you take the square root of it. Okay, so we have you practice that in WebAssign, okay, and see if you can do it. If you're having real problems with it, you can always ask me and email me, and I'd be happy to help. Okay, or we can do something on Teams. Okay, but I think most people could probably do this. Okay, give it a shot. All right, we're not going to probably have you though calculate that on the final. Okay, just see if we can do it in WebAssign. Okay, all right. So now let's look at the confidence interval. So we kind of looked at, okay, we see the point estimate. It's x bar 1 minus x bar 2. Now we have a standard error. Okay, that thing under the square root. Okay, now we can start constructing confidence intervals and test statistics to do our hypothesis test. Okay, so the confidence interval for the comparison between two population means is the following. Okay, and so just like anything else, all right, you have your point estimate, x bar 1 minus x bar 2. That would be your point estimate. Your t is your critical value. Okay, it's coming from the t distribution. Okay, and then you got your standard error. Okay, and so just like anything else, and then you take your critical value times your standard error, you get your margin of error. All right. Here's the thing. Is that, so just like I said, there's your critical value. Okay, here's the thing, is that the degrees of freedom, I want to tell you something. The degrees of, you think this formula is long? So remember, you need degrees of freedom to work with the t-distribution, right? Well, here's the thing, is that if you think this is long, holy cow, The formula, okay, the formula to go ahead and calculate the degrees of freedom for that t there is about 3 times as long as that formula right there. It is ugly. Okay, it's one of the few formulas that I don't have memorized. All right, I just allow a computer to calculate it for me. Okay, and so in other words, to calculate it, it's beyond the scope of, well beyond the scope of this course. Okay, so we're not going to have you calculate that. And so, do I think we can calculate the point estimate, x bar 1 minus x bar 2? Sure. Do I think that we could give it a shot to come up with the standard error? Sure. But to do the whole thing, the whole confidence interval, probably will allow the computer to do it because of that ugly degrees of freedom. Okay, and so one of the more important things that we're going to do for the two sample t-test is doing interpretations. If the computer ran it through, all the numbers and gave us the confidence interval for mu1 minus mu2, can we interpret what it means? Can we tell which one is larger, mu1, mu2, or can't we tell based upon our random samples? Okay, so that's what I want you to focus in on. Okay, and so this is really, really important, these next couple of slides. Okay, so if I subtracted estimates for two numbers, and I can tell you that the difference will be positive. All right, so in other words, I got two numbers. We're calling them A and B. If I tell you that let's subtract those two, okay, and I can tell you that the difference between A and B is going to be a positive number. Now just think about that. If you had two numbers, say 4 and 7, okay, make those A and B. Which one, if I told you that if I did the subtraction between the two, okay, A has to be the what? A has to be the 7, B has to be the 4, because when you do the subtraction between the two, it has to come out to a what? A positive number. So if I do the subtraction between two numbers and I can tell you that it's positive, okay, that's indicating something to you. Now let's read this. This indicates that the first number has to be what? Greater than the second number. Okay? Keep that in mind. This simple idea here, okay, is going to help us to understand how to interpret the confidence intervals. All right? All right, if I took two numbers, A minus B, but now the difference is negative. It's negative. Okay? Well, which one has to be greater in this situation? This indicates that the first number is less than the second, or if you prefer, that the second number is greater than the first. Okay? Hopefully that makes sense to you. All right, so if you had the numbers of 3 and 6. So 3 minus 6 is a negative 3. It's less than 0, right? And so which one had to be the greater number? The second number, okay? Seems simple, right? But that's what the confidence intervals are based upon, this simple idea. Okay, and then the third thing is real simple. If you took two numbers and subtracted them and you got 0 for it, what does that mean about A and B? They have to be equal, right? So keep this in mind, okay? Keep this in mind when we go ahead and interpret the confidence intervals. And I'll show you, all right? I'll give you a little bit more in depth here, okay? In-depth knowledge. So remember, we are creating a confidence interval for mu1 minus mu2. So actually, I'm not going to tell you, but if the computer tells you, the computer output, tells you that the confidence interval is entirely positive, okay, that indicates something. So let's read what it says here. A confidence interval for mu1 minus mu2 that contains only positive numbers suggests that mu1 minus mu2 has to be positive. And if it's positive, we then infer that, what did we learn before? That the first number, mu1, is larger than the second number, mu2. So, for example, let's say that from the computer output, the confidence interval for mu1 minus mu2 turns out to be 4,7. Now let's get something out of the way. All right. We are, again, not estimating mu1 nor mu2. We are not estimating those with these confidence intervals. Okay. So mu1 is not 4, mu2 is not 7. Let's get that out of the way. What are we saying? we are creating a confidence interval for mu1 minus mu2. We are trying to come up with that number that in the blue box. Okay? So what we are saying is that mu1 minus mu2 is somewhere between the numbers of 4 and 7. We don't know the exact number. Maybe it's 5. Maybe it's 5.2. Maybe it's 6. Maybe it's 6.8. Okay? Whatever the exact number is, we're going to note that it is a positive number. Okay, so mu1 minus mu2 is greater than 0. It's somewhere between 4 and 7. All right, so it's a positive number. What does that tell us? That tells us that mu1 has to be greater than mu2. Okay, so you can read what I have there. So if I subtracted estimates for two numbers and I can tell you that the difference will be positive, that means the first one has to be larger than the second. Okay, and so this indicates that mu1 is greater than mu2 anywhere from 4 to 7 units. So it could be greater by 4.1. It could be greater than mu1 is greater than mu2 by 5.8. I don't know exactly where it is, but the important part is that we know that the confidence interval for mu1 minus mu2 is positive, and that's telling us that mu1 is the greater number. Okay? So hopefully you get that. All right, let's move on. So a confidence interval for mu1 minus mu2 that contains only negative numbers suggests that mu1 minus mu2 is negative. We then infer that mu1 is smaller than mu2, or if you will, mu2 is the larger number, however you want to think of it. All right. So we look at the computer output and we see for a confidence interval for mu1 minus mu2, it turns out to be a -9 to a -3. All right. So hopefully we say, okay, I know that mu1 is not going to be a -9 and mu2 is not going to be a -3, right? What are we creating a confidence interval for? Mu1 minus mu2, that's always our parameter. It's always going to be our parameter when we run the two-sample t-test. It's mu1 minus mu2. It's not two separate parameters. It's one parameter. And we are trying to estimate that number there. Okay, so mu1 minus mu2 is somewhere located between a -9 and a -3. We don't know exactly where. Maybe it's a -8. Maybe it's a -7.2. Maybe it's a -4.1. I don't know exactly where it's located. But I do know that it's located between a -9 and a -3, and so it's going to be a negative number. And if I took two numbers, all right, and I could tell you that the difference is going to be negative, that's telling us something, okay? That's telling us that mu1 is the smaller number. Or if you will, mu2 is the larger number, okay? And that's telling us, this indicates that mu1 is less than mu2 anywhere from 3 to 9 units. Or if you will, mu2 is greater than mu1 anywhere from 3 to 9 units. And I said that right. Once you use the word less than or greater than, you can drop the sign. Just kind of trust me on that. Okay. So hopefully that makes sense to you. Okay. Let's move on. A confidence interval for mu1 minus mu2 could also contain the value of 0. This is our third and last option, possibility, I should say. Okay. So from the computer output, a computer says the following for the confidence interval for mu1 minus mu2. It turns out to maybe go from a -4 to a +6. Okay. So again, we are not estimating mu1 or mu2 by itself. So mu1 is not -4, mu2 is not 6. Okay. What are we estimating? We are estimating mu1 minus mu2. And we know it's located somewhere between a -4 and a +6. We don't know exactly where. Okay, so this is kind of interesting because this tells us that mu1 could be greater than mu2. Because now, how could mu1 be greater than mu2 in this situation? Well, it could be because our confidence interval part of it is positive, and so the difference between mu1 and mu2 could be 2, or it could be 4.8. Okay, or it could be 5.9. All right. And so mu1 could be greater than mu2. Well, what's another possibility? Well, the confidence interval is also the possibility for mu1 minus mu2, it could be negative. And if it's negative, let's say that mu1 minus mu2 could actually be a -3. Well, that's telling us something, right? That's telling us that mu2 is actually the greater number. Okay. Well, what else is this telling us? Well, what other value is in there? And that's 0. And so remember what we said when it's 0? That if 0 is a possibility, that mu1 could be equal to mu2. Okay. And so is the confidence interval sure about which one is greater? No, it's given us actually 3 possibilities. It's given us the possibility that mu1 could be the greater number, mu2 could be the greater number, or they could be equal to one another. So in other words, it's giving us inconclusive evidence. Okay, we are unsure based upon our random samples. Okay, that which one is larger. All right. So if 0 falls in the interval, okay, 0 is a plausible value for mu1 minus mu2, meaning it is possible that mu1 is equal to mu2. And ultimately, our samples did not indicate a significant difference between mu1 and mu2. So mu1 could be greater than mu2, mu1 could be less than mu2, mu1 could be equal to mu2. And do we know which one it is? No. We have, excuse me, we have inconclusive results. All right, and that happens. That happens to researchers all the time. All right. So those are our 3 possibilities for the confidence interval. If you got any questions, let me know. Let's get it out of the way as soon as possible. Okay. All right, let's continue. How about if we did a hypothesis test? Well, the hypotheses is basically the following: is that the null hypothesis is the hypothesis of no difference or no effect. Okay. So the null hypothesis will have mu1 is equal to mu2. Now, another way of thinking of this, and some students like this, all right, is that if you subtracted mu2 from both sides of the equation, you would get the stuff that you see on the right-hand side there, that mu1 minus mu2 is equal to 0. All right. So either way is technically correct. Okay. You can see how both are saying that both are saying that mu1 is equal to mu2. Okay. Now, how about the alternative? The alternative hypothesis, you have 3 possibilities. You can either have a greater than, you can either have a less than, or you can have a not equal to. And we're going to have to read the problem and figure out which one to throw in there. Okay, the greater than, less than, or not equal to. Okay, so we're going to expect you to be able to do that. So the null hypothesis will always be mu1 is equal to mu2, or if you prefer, mu1 minus mu2 is equal to 0. But then the alternative, we're going to either have to have a greater than, and it's always mu1 first, then mu2. So either greater than, less than, or not equal to. And we'll have to read the problem and figure that out. The conditions. I think the students make too big of a deal with the conditions. All of the conditions are is an extension of the one sample case. When we looked at a mean, looking at like a confidence interval or a hypothesis test for one population mean, it's all it is here. Okay, extended out to 2. All right, so you need independent random samples. All right, you need 2 of them. All right, 2 independent random samples. Neither sample has extreme outliers. Sound familiar, right? And then an approximately normal distribution for each group that is mainly important for small sample sizes, or we need that the sample sizes are 30 or more for the central limit theorem to apply. Okay, so in other words, we need x bar 1, okay, to be basically a t-distribution. We need x bar 2 to be a t-distribution, and when you subtract the 2 t-distributions, you get another t-distribution. Okay, is basically what it says there. Okay, I think students make too big of a deal about it. All right, if you take a look at the one sample case, all this is an extension of that. Okay. All right, here is the test statistic. Okay, now that was just kind of thrown out there. Sorry about that. I wish that didn't happen, but it kind of did. All right, fine. Here's the test statistic. Okay, here's x bar 1 minus x bar 2 minus mu1 minus mu2 with little 0 there. Okay, now where did this? So let's read this. When testing mu, okay, the test statistic was this. Where did mu sub 0 come from? Where did mu sub 0 come from? That came from so the answer is it came from the value in the null hypothesis. Okay, so in other words, where will the value for mu1 minus mu2 little subscript 0 come from? The answer is it's going to come from the null hypothesis. So remember how I rewrote the null hypothesis? We could either write it as mu1 is equal to mu2, or we could write it as mu1 minus mu2 is equal to 0. Well, the reason why we would want to write it like the one on the right hand side is because notice, let me go back. Notice that this guy up here, okay, mu1 minus mu2 subscript 0 here, we're getting that from the null. What's in the value in the null hypothesis for that? 0. Okay, so for the two sample t-test, this number right here always turns into 0. Okay, so in other words, the test statistic is x bar 1 minus x bar 2 for the numerator. For the denominator, it's your standard error that I showed you before. Okay, so that would be your test stat. Okay, how about the p-value? The p-value will be given by software based upon the t-distribution. Okay, so given by software. And then 5, the conclusion, smaller p-values give stronger evidence against the null hypothesis and supporting the alternative, right? And so we always compare that to alpha, right? So we'll go ahead and reject the null if the p-value is less than or equal to the significance level, just like we always have. That never, ever, 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 ever changes for any hypothesis test. You always compare the p-value to alpha, the significance level. All right. Probably we're going to, in the end of the class here, leave the significance level at 0.05. That's where most industries have set it. That's where we're going to set ours. Okay. And then obviously do not reject the null hypothesis if the p-value is greater than alpha. Okay, so there's your steps for the hypothesis test. And that takes us to the end here. So in part 2, we will actually run through the confidence interval, the what I expect you to know, okay, and be able to do, especially with the interpretations, set up the hypothesis test, the null and the alternative, maybe confirm a condition or two, right? And then we should be able to interpret it based upon the p-value, okay? So your calculations on the final for section 10.2 only, it's going to be limited, okay? We want you to be able to interpret this stuff from a computer, okay? And so that's what you want to concentrate on. All right. So thank you for your time, and hopefully you have time to check out part 2 here. And so I'll be talking to you then. Thanks.